In this example, you can see the three types of relief devices. I have a cryogenic fluid inside a vessel, and because of the heat linking with the environment, although I have insulation, I can have vaporization of this fluid if for any reason my customer stops withdrawing liquid from the process. As I have no withdrawal of product, my vessel will fill until I reach the maximum level available or permitted in this equipment, and I will stop from giving or from feeding cryogenic fluid to this vessel. So if the cryogenic fluid is stagnated inside the vessel and with the heat leak, I can have the vaporization of the fluid, and to not get above the maximum allowable working pressure of the vessel, I need to release this pressure. I have three types of way to doing that in this system. The first one is using the indirect actuated valve. So my pressure transmitter is reading the vapor phase of this vessel, and it sends the signal to the PIC, pressure indicator controller, that have a set point to send the signal to the control valve in order that it will open to release the pressure. If the opening of the control valve is not enough, my pressure will keep increasing and I will reach the set point of the safety valve. And in this case, my safety valve orifice will open and I will release also the pressure. See that this type of relief device is the direct actuated valve, because the pressure of the fluid is responsible for opening the orifice of the safety valve. If for any reason my pressure keeps increasing, I can reach the set point of the rupture disc, and the rupture disc will be responsible for releasing the pressure of the vessel. One of the reasons to increasing the pressure inside the vessel, for instance, is that my control valve can fail. It fails, for instance, the instrument air fails. I have a fail close valve, so this will close, and I will not be able to release the pressure from this point. And in fact, I don't want to lose product from my system. That's why it is a fail close. And that is not a big issue because I still have two types of relief devices to release my pressure. My safety valve can be sized for the heat leaking case, and my rupture disc can be sized, for instance, to add the additional flow required in a case of fire case. So in this case, it's possible to have different types of relief devices in the same system, and we can use also them in conjunction, that you will see in this video. And just to finish this example, I have here a diverter valve that is responsible for letting always a set of relief devices available for relief the pressure. So my diverter valve will work aligned to the left side of my set, or it will be aligned to the right side of my set, where I have the safety valve, the rupture disc, and also a vent valve. Why I have this vent valve? Eventually, I will need to do the maintenance of the safety valve and also of the rupture disc. And this branch here will have the same pressure at the vapor phase of the vessel. So I need to change the position of the diverter valve to the other side, and to be able to remove the safety valve or the rupture disc, I need to open the vent valve, depressurize this branch, and with that I have safe conditions for my operator or for the personnel, the maintenance personnel, to remove this. And once everything is okay, I add again the devices for its location, and I'll close the vent valve. As you can see from this example, the different types of relief devices will have different set points, and I expect that the control valve set point will be lower than the PSV set point, that will be lower than the ruptured disc set point, and it's defined based on standards and guidelines. We have seen an example of the three pressure relief devices where the ruptured disc is a kind of bursting disc.